Okay, welcome to this class. Today is the second class that we will go over, and in fact, the last class will go over graph computation or analytics with graph data. Yesterday, we started with the conceptual framework that if you want to model relationship, if you want to focus on entities, but instead of focusing on entities attributes, like for example, instead of focusing on students' height and weight, we would focus on the interpersonal relationship, or who knows who. And this is of course the ubiquitous social network application. And I probably used social network as an example several times in yesterday's class. Having said that, the framework is a lot more general, okay? And I think I alluded to the fact that if you think about it, chemical bonds can be viewed as a graph, right? Except, there's an identity associated with each node or each vertex being the chemical element, okay? But certainly it is a graph object, because when you say carbon dioxide, it's not just one carbon and two oxygen molecule. It's also the topography or the connectivity, all right? So the representation of carbon dioxide is not just one C and two O's, even though that's how we write it in English. In fact, when you see CO2, what's implied is that C is sort of like in the middle, and there is a bond, chemical bond between carbon and oxygen, and also another one with another oxygen. All right, so carbon with oxygen on the, say, left-hand side, and oxygen on the right-hand side. And there's a little bit of a bend, so it looks a little bit like, I guess, Mickey Mouse head, where you have the head and two big ears. You can think of the Mickey Mouse head as carbon and two big ears being location of the oxygen molecule, right? So now, with chemical bond, the geometry does matter. Geometry does matter. So the degree between let's say the bond between the first pair, carbon and oxygen, and the second pair, carbon and oxygen, that is meaningful, okay? But in our case, in graph, we go for less than that. We just say that, well, right now, we just want to say that carbon is connected to oxygen, and it's also connected to another oxygen, but the two oxygens are not connected, right? So if just to be sure, oh, I haven't shared the screen. Okay, never mind. Okay, so right. Okay. So when we say CO2, okay, there's one of these and there's two of these, right? And in real picture, it kind of looks like this. Let's say O. I think it's like that, right? Now, in chemical model, it does matter which degree that is, okay? It does matter. But in our case, all we want to say is that this is one node, and this is another node, and this is another node, okay? So it's not as informative as this. So the degree doesn't matter. The representation doesn't really matter. I could draw it like this. I could draw it like this, okay? What matters is that there's a central node that's connected to the two nodes, but the two nodes themselves are not connected. Now, in future application, like with graph neural network, there could be a label, like this is a carbon, this is an oxygen, okay? But for now, yesterday, we dealt with homogeneous case where this is generic item. Okay, this could be a person, this could be a person, this could be. There's no distinguishing feature. Okay, what it means is that we were not addressing node attribute. Okay, and in fact, today's class we won't address that either. Reason being that you've had plenty of times to focus on node attribute, because in fact, if you think of node as data point, all your tabular data is all about node attributes. Okay, so that's something that you've been doing all this time is studying the vector information about individual data point. Okay, so yesterday we were focusing on the relationship between these. So that's where the graph data. Okay, so do understand that I guess I can draw you a picture that is the most general picture. Hold on, let me share. Okay, and let me start the paint. Okay, so now we have a blank screen. Oops, why is it not sharing? Hold on. Let me share. It's not updating for some reason on the screen. Hold on. Yeah. Oh, it has to go back to yeah, sorry. This one. Okay, good. Okay, I'm going to draw, I guess, the most general representation. Okay, so look at the screen carefully. Okay, this is you. Oops. Oops. Happened here. Không cần các bạn, sorry. It's not sharing, so log in. No, not no. Reason, I don't know, maybe. Oh, no. And input. Oops. Sorry. Now we're back to annotation. Okay. Good. Okay, this is the most general way of modeling your data. Okay. So yeah, I just draw two persons to designate this is one data point. Okay, the person is a vector. The person is a vector. Okay, defined by all the node attribute you can describe. Excel form. In Excel form, this is right. Now, because everybody is connected in a network, there is this information. So that's a matrix. Okay. Do I have vector? Vector of A, B, C, D. This is A, B, C. So vector, vector, vector. There's also a matrix. But not only is there one matrix, there are many relationships. It's called multiplex relationship, right? So this could be relationship in Facebook. Maybe there are a relationship on a, I don't know, line group or whatever, doesn't matter. So there's actually a whole bunch more matrices. What it means is that in theory, if you have n persons or n data point, okay, n data point, how many values are you going to record? Okay, let's do this. Let's just say I need one value to record the name. So this would be like student ID. Okay, student ID. Okay, so if there are 100 students, there are 100 student ID. Okay, each student ID is a vector of dimension D. Right? Each student is a vector of dimension D. So this could be your height, your weight, your age, whatever. Right? Now, let's imagine that of the 100 students, okay, there are M relationships. So in other words, each of you can know each other in one of the M channels. Okay, so M could be Facebook and I don't know, a line group or personal connection, telephone, I don't care. Okay, the point is that how many values are you going to have for that connectivity? Well, each time you're going to have another n number, right? Well, actually n plus minus 1, but I'm just going to make it n. Okay, it's n minus 1. Okay. Not only that, because there are that many dimensions. Okay, so these are the number of values. So if you have 100 students, each one has one name. Each one, I know you guys buy a vector of 7, name, age, age, weight, height, or whatever. And then you have 3 channels for knowing each other in school, in social network, and back home or whatever, okay, or position. So maybe 3 times 10. So this is actually a rough calculation of the number of, well, number of numbers that you have to record the data, okay? So that's really what we're talking about. Now, in our class, okay, and today, again, like yesterday, I was focusing on the node attribute, right? I wasn't focusing on the node attribute. I also wasn't focusing on individual identity, okay? And I only study one relationship at a time. So essentially, we're down to just one matrix, okay? So that's our focus today as well. So yesterday we had this big thing, which is very important. It's called adjacency matrix, okay? Adjacency matrix, it's a matrix of zeros and one. If I say adjacent matrix, that means it's unweighted. It doesn't have weight. If I have a weight assignment, for example, a degree of how well you know each other, you know, good friends or not, or you're not good friends or whatever, then I would use W for weighted adjacency matrix. Okay. And what else do you remember from yesterday? What else? The matrix can be what? Can be what? It can be symmetric or asymmetric, right? If it's symmetric, then, you know, it's like this. So if I and J, I points to J, then J points to I. Okay. And most of the time, what this really means is that if everybody has this relationship, then you might as well say this relationship is mutual. So when you have relationship that you say that I and J just have unweighted. Okay. Now, again, let me emphasize the fact that you could accidentally have this, where if I knows J, J knows I, not by design, but it just happened to be the case. Okay, in which case you still think of it as a directed connectivity. It just happened to be mutual. Okay, but in application, you will always make a decision. Make a decision that what kind of matrix are you talking about? What kind of graph are you talking about? Okay, so you have to make, well, you have to make decision whether or not it's 0, 1 or weighted. You have to make decision whether it is undirected graph or directed graph. Okay, so if it's undirected graph and you draw a matrix, adjacency matrix, you will see that this element and this element completely the same. So if you draw this kind of line, it's exactly symmetric. Okay, so we have this thing where it's have adjacency matrix or weighted adjacency matrix. You have undirected graph, directed graph. If it's a directed graph, then some I to J, but J doesn't go back to I. Okay, again, the analogy is if you know a famous actor or actress, that famous actor or actress doesn't have to know you. Same with following on social network. Okay, what else can happen with this? Well, if I draw the graph, a situation where everybody at some point can be reached on that graph. It's like, you know, it's like everybody is connected somehow. Okay, not directly, but indirectly. And there's also a situation where it is unconnected. So you have maybe like a network here and a network here. Again, what's the implication? If you want to get the message across to everybody, if it's completely connected, then in theory, you can sort of like start a rumor here and eventually it gets everywhere, let's say. Okay, let's see. But there is also something more subtle, which I mentioned, which is called cyclic and acyclic. Okay, but that's a little bit more detailed than I wanted to go into. Okay, but I did show you what it looks like. This concept about, you know, this same piece of information keeps making the round on the internet, it goes back and forth, and you get it, and then you get it, it goes round and round. That's sort of like the anecdotal evidence of the fact that it's cyclic graph. Okay, it cycles back. If it's acyclic, then it doesn't come back. So it would be something like I give a message to you, you give something else. Okay, this connects the whole set, but it doesn't come back. There's no feedback loop. It doesn't go round and round and round and round and round. Okay, so that's a little bit more subtle. Okay, so those are the basic concepts that could property that you could look at and analyze vis-a-vis the matrix and the graph. And that has different implication on the application. But so far, it's strictly what? You're just looking at the graph or the matrix. Okay? There's nothing more. You're not doing any kind of computation. You're not doing any kind of analysis. Okay? So that's sort of like the first half of yesterday. Then the second half of yesterday, I introduced the notion of kind of network positional relevance or positional importance or critical component. Or, you know, in this case, you can see something like, you know, this guy is on the periphery, doesn't matter much, this guy matters more. And this concept is is what I summarize as the concept of centrality. Okay. Now, computationally, what the centrality means is that you take an adjacency matrix, which is n by n, and then you compute a vector n, where this is some kind of scoring or weighting scheme. Okay, so centrality analysis in terms of ultimate computation, it's like you take a matrix n by n information and then reduce it to this information. But you're not actually capturing the whole information. You're just sort of like trying to measure some kind of importance. And how this is done is arbitrary to an extent. It depends on what you mean by important. And I say, what does important mean? Important mean you are important if you are connected to somebody who's important. Okay, so that would be something like what? That would be that vector centrality, right? Also cats, also pH rank. This is kind of like similar, very similar in that sense. You are important in a network because you're connected to somebody who is important. So that's really very important, very powerful. Less powerful than that was the original thinking was, well, how important are you? How many people you know? Just pure counting. And that was known as what kind of centrality? You know that degree. Centrality, right? Why it's called degree centrality? Because in graph theory, number of edges is called degree. That's it. That is inherited from that. And finally, if you say number of times the shortest path runs through you, then that is betweenness, right? So three family or three types of criteria is what gives you different assignment. And then we ended that yesterday. Okay. Now, okay, go back. Today is promise. Today is about, well, some application. Okay, so application. Oh. Right. Okay, so today's application day, so to speak. Okay. Now, this is actually from an old talk I guess I gave back in 2018. This was this was I don't know if you know this, but people who do a lot of data science tend to use Python a lot. And every year or so, they get together in a conference. It's like a PyCon or Python conference. It's not strictly speaking a conference on data science, but being that most recent application that's written in Python is about data science, of course. You know, I was kind of, I guess, invited to give this talk. Okay, so this is about well, first of all, the address was to a room full of Python programmer. So example that I use in this case here would not be mathematical code, it would be Python code. But the importance for us is not that. The importance for us is that we walk through different situations that you can imagine in practice. Some of it's a little bit more trivial and artificial, but this is about, you know, how would your application problem look like? So I'm going to skip this. This is sort of like motivation. If you saw the video that I asked you to watch, this about the 7 bridges of Königsberg. Well, the whole significance of this was that like my motivation about graph data, it's about representing reality as a graph. Okay, so in this case, graph object, meaning here on the left hand side. So you can see this is the graph, right? So instead of focusing on different part of the city of Königsberg, you just think of this as a node, and this is an arc, or this is a vertex, this is an edge, same thing, okay? And so you draw it like this. So 2 bridges mean 2 arcs. This is the middle island, so that's this vertex here, the vertex, okay? And it's kind of like a riddle in the, I guess, early part, like 15 or 16 years back in the, hundreds of years ago. The question was, can you actually cross 7 bridges once? Or not once, but you cannot like repeat. You cannot repeat the path, something like that. Okay, so so the result is that once you map into this graph, then you translate into 2 things. Okay, 2 things. If you are going to go up and leave, that means that they're coming and out. Okay? So if you think about it, each node can have even or odd degree. Remember the word degree? Okay. So the idea here is that you can have 2 situations. Okay. All the you can keep going back and forth, you know, sort of like completely cyclic, going round and round and round and round. That would mean it's like every node has even number of edges, so even degrees. Or you can have a beginning and an end node, each of which would have odd number, odd degree. Okay, then you can do that. You can travel a path and not repeat the same bridge. However, in this case, you will notice that the city of Königsberg only have 1. Okay, so the fact that there's only 1 odd degree node means that this problem cannot be solved. Okay, it's proven it cannot be solved. Okay, so the solution was that there's no solution. Okay, now eventually, I think what happened was 1 or 2 of the bridges got bombed in World War I or something, or World War II, I'm not quite sure. Okay, so eventually the number works out so that you can perform what's called Euler tour. Okay, so anyway, that's got not too much, doesn't have much to do with this, but it has to say that there's a lot of power with analytics when you abstract from reality to a representation. Okay, except in this case, the data is not big, it's only 7 nodes. Okay, so now this is more of the application that that the talk was talking about. And I don't know if you can see this. Okay, this is about the motivation. This is a quote from Rudolf Haldane. He's you know what the central bank is, right? Central bank, like the Bank of Thailand, is the bank of bank, controls the stability of the financial system. Well, you can read the quotes here, but basically what it means is that because the financial system, modern financial system, are so highly interconnected. Okay, so once you hear the word highly interconnected, what's the hint? Network effect, right? Highly interconnected. What it means is that it makes everything better, more efficient, because you know you can liquidity, meaning money, can flow through the system easily from here to there, everywhere. So it's good, it's efficient, it's quick, it's convenient, it's better, it's better. However, it's also more fragile. So if you think of unconnected system, if something is wrong with one guy, there's no contagion. It's very local. Okay, so this interconnected financial system, meaning it means that all financial system, banks, insurance, credit unions, pension funds, your own money, somebody else's money, the university's endowment fund, everything is all connected. So it's more efficient. You can, money can flow, but it's more fragile in the network sense. That is, if something happens to one bank, it can draw problem with everybody else. Okay, so with that, you can think that different topology. So you can just look at this. Imagine, okay, if these were banks, okay, and the arrow represents some kind of dependency, like borrowing or money flow. You can imagine that in this case, right? Let's say in this case, if something happens to this bank, then the rest of the bank can maybe operate fairly okay, can get around it. But if this were the topology, and this is extreme case, nothing is like that. But if this were the case and something happens to this bank, what happens? Everything shuts down. Okay? So connectivity is a wonderful thing, but it's also a terrible thing. It's the same thing like social network, right? It helps facilitate information flow, but it also, can have a very bad side effect. That's what this means. So with that, okay, with that, one of the applications that we built on was, I guess, summarized in this paper. Right. Oops. Okay. So this paper essentially look at the interbank system. Okay, I'm just going to skip all the math here, but here's the picture. Okay, here's the picture. You can think of each line as representing 1 billion baht worth of interbank. Okay, and these are the banks that was analyzed. That this was when I was in the Bank of Thailand, so I had access to this. Okay, outside of Bank of Thailand, you don't have access to this. Because of that, I don't name any names. Okay, these are generic 1, 2, 3, 4, 5, 7, and it's also very old data, so it's not sensitive. Okay, so these are actually two different networks. This is the Thai baht borrowing, so you can see it's more homogeneous. Everybody's lending to everybody. But for the US dollar, there's actually foreign currency activities. It's a little bit more skewed. Okay, so it's not evenly spread out. It's a little bit like yesterday when I was drawing the random network. It looks like this, but the network of actresses or characters in Les Miserables musical, it looks a little bit more featured. It's a bit like that. So anyway, so this is real number, but very old data, so it's not sensitive, and it doesn't name any banks. Well, the gist of it is, by looking at this and using eigenvector centrality, much like the one that we saw yesterday, this was the analysis. Now, so all the banks are listed here. I just gave them silly names like colors, okay? Okay, so it's an alias. If traditionally, you want to say who's important. So imagine, okay, look at this. Which one do you think is the most important? You. Okay, from the green side, which is the most important bank? 1, 2, 3, 4, 5, 6, 7. It's this guy, right? This guy, right? It turns out that in terms of volume, analogous to degree, okay, this guy is important. So on a naive basis, the Bank of Thailand systemic risk monitoring the systemic perturbation to the system, right? The risk of the crisis, they would focus on this guy. And if this bank is in trouble, the Bank of Thailand would try to what's called inject the money. Basically, it's not giving money away, but sort of like sticking money here. Okay, that's actually the wrong target. Because even though this is a big activities center, it has very little network leverage. So it's not likely to pull everybody else down. However, this guy is very important. This guy, even though, you know, in terms of volume, it's half of this guy. But in terms of network leverage, who's the most important? Is this one. Okay, this is bank. Okay, so in fact, if the Bank of Thailand wanted to monitor and make sure to intervene by injecting the money, okay, so like let's say there's an external shock to the system, every bank has a hard time. The Bank of Thailand should not look at this guy. Well, should look at this guy, but not only this guy. In fact, the priority should go to which one? That guy. Okay, and that's you know, proposed in the Bank of Thailand. And now if you Google search, internationally, it's called Domestic Systemically Important Bank. Okay? And this is something that the Basel Committee of Banking Supervision has come to view. So this is very real. This is very, and that's bad. Okay. And this is now this is US lending network. It turns out that the one that has a lot of volume also has a lot of network leverage. So in this case, happens to agree the traditional and network theoretic analysis. But network theoretic analysis also points to this guy who barely registered any transaction, but actually has, you know, just as nearly as much. So anyway, so this is a real application. This is, you know, it's not just, but of course, then I went on to talk about some other example. This one is also another interesting example, but this is, yesterday, you guys remember that I mentioned that quality matters a lot more in terms of logistics. Well, this is how it looks like. Okay, so if I take, this is a city of Bangkok, right? Gongthep Mahanakhor metropolitan. And I say each district has a neighbor. So one means this district has a neighbor with that one. So for example, Thai here has connection with, I can't read, Bang Su, I think, yeah. So anyway, so that's the matrix of connectivity, 0 and 1, okay? Obviously, it's symmetric because neighbors are symmetric, okay? Now, I ask you, can we draw this, instead of like this, can we draw it as a graph? Yes, that's next slide. So this is actually how the different districts are drawn, right? So you can see where do we live? So this is Pathum 1, this is Klong Thai, this is Bang Khun Thien. It's obvious, right, that Bang Khun Thien sort of like on the edge. Now, in terms of importance, logistics, if I say, you know, everybody wants to travel from here to there, from there to here, everywhere. The question is, in terms of, let's say that this is like a distance, kind of, okay? So if you're going from Don Mueang to Yanawa, now, technically, maybe this is the shortest path, but if I define the shortest path as minimum number of transportation hub or minimum number of district I have to go through, right? You guys know what shortest path is. And that happens in real logistics. A lot of time, it's not really the physical distance, it's the hub to hub connection. Think about it. When you transfer from ship to land, that takes a long time. That takes a long time. It's not a long distance, but it's actually very, very critical because you have to take the cargo from the ship to the land, whatever. So analogous to that. So if this is a path, for every travel path, you consider what is the minimum or the shortest path. From here to here, from there to there, here, there. And then you count how many times out of all the possible shortest path goes through this city, this district, versus on that district. If you did this, then you would get centrality. I think if you just count numbers, the jump has more. Okay, this is called degree centrality. But if you count betweenness, you go to this guy, betweenness. Now this is the big picture. Look at this. Clearly, there are two districts in Bangkok that matters more than stands out. And yeah, one is Jatujak. But you know what? Number one is not Jatujak. Anybody guess what it is? Which district? Dusit. Dusit is a district that you have to go through if, assume you want to travel from every district to every other district, okay? Now, obviously, you can do some kind of calculation that is biased. In other words, you can say that for your company, you are more focused. For your company, you're not traveling from any district to any other district. For your company, these are the district of your clients or your distribution center. These are the district of your factory. Then the number will be different, right? But can you do the same thing? Yes, you can. Yes, you can. So this betweenness centrality is extremely useful. Naively, it means, counting the number of times, the number of shortest path that goes through a city for any path. But in your application, you don't care about any path because you care about here and say here, because here is your factory, here are your client, here's your client, here's your client. Then your betweenness centrality will be very different. Okay. But you can see right away that this reveals something very, very extreme, right? All of a sudden, Dusit became something that you have to consider. So, and you can use all kind of measure. And this is like the graph we saw yesterday, where using different centrality, it would give different results. But it should not surprise you that the top significant or the top centrality significance districts are kind of like similar. So there's a lot of correlation between different criteria. So that would be one example of a logistic. Okay. Now, just to give you a flavor, this is how you would use it in Python. You have to, first of all, Python doesn't allow you to do this kind of network theoretic easily. You have to import the library called networkx. Okay. And once you import networkx, you can sort of like do calculation. For example, there's nx.eigenvector underscore centrality. So that's the same thing as when we type in that eigenvector at the map. Okay. In fact, networkx is quite a very, very easy software to use. Okay, not software, program. Right. So that would be something like, yeah, you have the data, you make the graph, and you make the analysis. Okay. Now, this is something that's, well, a little bit more contrived. Back then, I think this was 2018. I don't play games. I don't know if you guys play games, but apparently in 2018, Overwatch, have you guys played that games? I don't know. Maybe it's too old now. But Overwatch was a popular game. Now, here's the thing. Here's the thing. When I talk about neighborhood, adjacent district, it's symmetric, right? In this case, it's not. This is kind of like relative strength index. In other words, all the Overwatch character, I don't know, Raja, Zenya, I have no idea who these guys are. Okay, these are computer games character. There is a relative strength index. So this guy has a strength of 20 over Reaper. But Reaper has a strength of 1 with Sarah and McKee and God knows what. So clearly this is asymmetric. Okay, so this matrix is number 1, asymmetric. Number 2, is it just adjacency or is it weighted? It is weighted, right? It's weighted. Now, this is where eigenvector centrality comes in very much, right? Because this is your strength versus your enemies. But if you have weak enemies and you're strong against weak enemies, that doesn't matter much, right? So what you want to have is strength against strong enemies. And why or how do you measure the strength of your enemies? They themselves have to have strength against strong enemies. And their enemies, how do we know they're strong? Because they have strength against their enemy. So it's a recursive equation, right? And remember yesterday we talked about recursive equation, ax is equal to x, the word same eigen, right? So this ends up being the perfect case for using eigenvector centrality. And so based on this, if I were to play computer games, by the way, a lot of computer games are really ripe for hacking, if you knew how to do this kind of technique. Oh, I think I didn't reveal. Did I reveal here? Yeah, apparently I didn't spoil anybody by revealing who's more important, but in the paper, in the algorithm, obviously, it would say something like, if I remember, I think the name Zendaya kind of stuck out for some reason. So that could have been the strong character or weakest, I don't know. Okay, but certainly I didn't reveal it on the transparency. Okay, so that's it. Now this was the case that we talked about. Okay, so this is this one I'm not gonna cover it again. Finally, well not fine, yeah, finally, this is good. Finally, there's this thing. Okay. Oh, Kevin, well, you guys are too old. I'm too old. Yeah. You don't know who Kevin Bacon is. Okay. Anyway, he's an actor. Even before that, there's this guy named Erdos that nobody even knew. Well, the name is Erdos. That's the mathematician. But then mathematician wanted to communicate the concept. They didn't know how to do it. So they picked Kevin Bacon. Okay, so this was when mathematicians tried to communicate to the general public. So picked Kevin Bacon. Well, here's the claim. The claim is this. You know how Hollywood, well, like in Thailand, the movie scene, sort of like all the actors eventually act together. Okay, so now in this case, there are two kind of entities. Originally, we talk about peoples or cities, right? Now there are two groups of things. There are actors and movies. Okay? So two different kind of nodes, very distinct, very, right? Now, Kevin Bacon number works like this. If Kevin Bacon and you acted in the same movie, you have a Kevin Bacon number of 1. If you don't act in the same movie as Kevin Bacon, but you act in the same movie as a guy who acted in the same movie as Kevin Bacon, your Kevin Bacon number is 2. In fact, we could have used this for the Les Miserables yesterday, but okay. But this is more popularly used example. So you can see here. Okay, here this is very important. The claim was nobody in Hollywood has Kevin Bacon number greater than 6. This is what's known as small world phenomena. Okay, there are thousands of actors in Hollywood, but eventually you can link them. You can link them with 5 movies. And just to show how crazy that is, Bruce Lee, you don't think Bruce Lee had anything to do with Kevin Bacon, but it turns out Bruce Lee acted in this movie, I don't know what that is, with this guy named Kenneth Tobey. I don't know who he is either. But the fact is, this guy, Kenneth Tobey, acted in this movie, Hero at Large, with Kevin Bacon. So what's Bruce Lee's Kevin Bacon? 2, right? 2. That's the connectivity. Okay. Now, technically, this graph is known as bipartite graph. Bi means 2, partite means part, the 2 part. So it's not just one graph, it's actually set of nodes. So yesterday we were drawing something like this. Oops, again, I did this. Panic. Okay. Okay. Annotate. Yes, the graph looks like this. V is a collection of, graph G is collection of V and E, right? Right? Where E is a connection from one vertex to another. A bipartite graph has like this. Bipartite graph is equal to V1, V2, and E, where vertices within V1 are not connected. Vertex and V2 are not connected, but vertex between V1 and V2 are connected. Okay, so with that, you can always draw V1 over here, V2 over here, and then be aligned. Okay, this is called a bipartite graph. Okay, very important. Now, this is one of the most important thing, powerful tools. You can start with a bipartite graph and end up with a graph like this. How? Well, think about it. This is Bruce Lee. Okay, this is Kevin Bacon. This is Bruce Lee, right? How many times do they have to go through this to see each other? 1, 2, right? So now I create another graph that say Bruce Lee and Kevin Bacon and add number 2. So by having this, now this, by the way, is a matrix as well, right? It's a matrix, right? It's a matrix of movie. So if you think about it, this is actors, this is movies. Okay, this is 1 or 0. So you actually have this matrix. Okay, this matrix looks like this. Movies, actors. Okay, but by doing this kind of computation, say from Bruce Lee 1, 2 to Kevin Bacon, I can make this into another matrix, which is actor and actor, and then I put number 2 over here. Right? This is very powerful. It's the second most, well, I don't know, it's the second most. Just like in network analysis, centrality is very powerful. This ability to go back between bipartite into just a regular square matrix is very useful in practice. Okay, why? Why do you think that is? Well, you guys, well, it's very simple. You stand over here. That's one group of entities. What about here? This could be products set. So instead of having actors on one side, on the other, we can have customers group on one side and set on the other. And the ability to find similar between two customers based on profile in their products is essentially what all e-commerce is built on, right? So, platform like Shopee, Lazada, God knows Amazon and all that. Okay? So this is very powerful, very important. And by the way, it's very easy to do. You just sort of like transpose this matrix and multiply. But anyway, so what happened is we did this, and we make the calculation. So the data comes in a rectangular matrix. By the way, do you know this guy? No? Okay. Yeah. But this guy is a monster. He has a Kevin Bacon number of 1. Because there's a movie called Tremors. Apparently it's a cult movie where this guy lives underground and attacks people and Kevin Bacon. So this guy has a Kevin Bacon number of 1. Okay. So we go on and say, okay, fine. How about this? Now, this is the detail. These are names of, can you guys see this? You can't see, I'm gonna read for you. This is Tom Hanks. Tom Hanks is a person, he's an actor. So is Tim Allen. So is Jim Banning, I don't know, okay? Notice that, okay? These guys are not connected to each other directly. They always have to go through movies. So when you draw, in fact, a nicer way to do this would be to color it, okay? So maybe movies would be in blue and actor would be in red, okay? But actually, remember about embedding, you can draw this any way you like, okay? This is not the way they plot bipartite graph. The way they plot bipartite graph is called bipartite embedding. It looks a bit like this. It's not as nice to look at here, okay? Basically, movies here, actors over there. Movies, actors, okay? So, somewhere in here is Tom Hanks, links to Toy Story, and goes back to Tim Allen. It so happens that not only do they have one connection, they also have another. Tom Hanks was Toy Story 1 and 2, so it's obvious, right? So now, this is the construction we did. Now, I don't care about movies. So I take and I create actor to actor numbers. Now, in this case, it's not Kevin Bacon number, it's everybody's number, right? So it's a link. It's a Kevin Bacon number is how many movies does it take to link one actor to an actress to Kevin Bacon. In this case, I'm going to create that matrix of number between any two. Doesn't have to be Kevin Bacon now. In fact, he's just 1 of 1,000, right? So I create that strength. By the way, this is just a small shot, and this is more. In fact, this is the data set. The real data set has 14,000 nodes. 14,000 nodes. That means the number of actors and number of movies bind together. And these are the edges. Okay, so these are the pair of actor and movie. Again, this is still bipartite. But anyway, I just want to show you that, yeah, you can plot the thing, but it doesn't. So this is real data. I think it's from IMDb or something. Okay. So I, out of this, created connectivity matrix, okay, between two actors. So let me ask you a question. Is this matrix, the resulting matrix, is it going to be symmetric? It's exactly the same. remember I told you that I'm going to put a lot of weight on the exam on graph theory. It's a little bit like this. Very easy. Just to say, based on this kind of data, is the matrix going to be symmetric? Is the graph going to be undirected or directed graph? Well, in this case, what do you think? Undirected, right? Because if Bruce Lee is connected to Kevin Bacon, then Kevin Bacon is connected to Bruce Lee, right? Completely symmetric. Completely symmetric. Now, is it weighted or unweighted? Obviously, it is weighted, right? Because the number differ, right? So between Bruce Lee and Kevin Bacon, the number is 2. Okay. Between Tom Hanks and Tim Allen is 1. Okay. Now, do I want to use that number? Do I want to use that number as weight? Actually, think about it. The bigger number doesn't mean the closer they are. It's the opposite. In fact, the smaller the number, the closer they are. So instead of using the matrix of numbers, I'm going to use, say, matrix of 1 over that number. Okay? This is a heuristic, just to convert something to. So actors that are close together, again, then you can do this centrality, and I can ask in the network of actors and actresses, who is the most important? Who's the most central? What do you guys think? You think that if I'm to plot the centrality score from highest to lowest, what's it going to look like? It's going to kind of even, or it's going to kind of be like this? Well, this surprised me completely. Because this is what I got. In other words, look at this. Centrality of all the actors are kind of like different, not drastically different. It's kind of linear rather than this. Then there's one guy based on eigenvector centrality that's more important than anybody else. It's like he appears in a lot of movies with a lot of actors and actresses who appears in a lot of movies, and eventually he links everyone. Okay, this is not something I expected from Hollywood. Maybe Thailand, maybe you have one guy who's like dominating. In Hollywood, you have a lot of alpha or A-list celebrity, right? Male and female. Well, what's not surprising is that the A-list celebrities are here. It's also not surprising that a lot of them are males. Okay, but what's most surprising is that there's actually one guy who's more central in Hollywood than anybody else. Okay, you want to guess who it is? Who? But it's not Tom Hanks. Tom Hanks is close here. But it's not Tom Hanks. Who do you think it is? You don't know. Okay. So, see, go all the way here. The second one is Sean Penn. Sean Penn, by the way, is number 2. But still, he's like here. And Ed Harris. Ed Harris is quite important. You notice that Ed Harris, he's not a lead character, right? But he does appear in a lot of movies as a sort of like maybe a second most important character or something. So, but this guy stands out above him. Yeah. So that's that. Now, before we go on a break, I just want to show you this little paper that we did with your TA here. Basically, we look at financial market variables, Thailand financial market variables, creating some kind of this is a very good, by the way, you should do this on your project if you have a lot of variables. Basically, what it is list all the variables you have, and for each pair, do what's called a scatter plot. Scatter plot. That gives you an impression of where things are linked. So you can see that a lot of them are not related, but you can see that, yeah, there's some kind of like a negative correlation, positive correlation. And so I would really encourage you to use this kind of visualization. So this is a scatter plot between two random variable. On the diagonal is actually the histogram, right? And then this also is a measurement. Now, in this case, for example, I do the scatter plot. There's a kind of attempt at drawing a line inside to say which direction, so forth. If it's like this, then usually it doesn't have much correlation. So let's say we calculate correlation. Instead of looking at this picture alone, we look at the number, which is be up here. You can see this? This is emerging market Asia equity. Remember that? Emerging market Asia equity, meaning stocks in Asia. And what's this? This is SET, that's Thailand stock. So they have very strongish, not that strong, strongish correlation. So here is a scatter plot. And this is the value of their correlation, I think 0.56 or something, okay? So this is the value of the correlation. There's actually a dot that, underlines the size. So at a glance, you can spot that of this 14 variable, there's kind of strong correlation here, and it's signed, so it can be positive and negative. Okay. Well, the idea here is that based on this, you can do centrality analysis. And although we didn't do centrality analysis on this, we did centrality on what's called copula significance, but that's beyond this class. The point is, based on certain adjacency, and you analyze it using cat centrality. Remember, cat centrality is a little bit like eigenvector. Anyway, it says that what's happening here is a lot of time driven by S&P 500 and emerging market bond index. Okay, so this is something real. So in a way, you can start with something that looks like this, which is a matrix, right? And end up with something like this, which is a vector, right? Remember, remember, these are all the variable. So if it's circular, so if I stretch it out vertically and take the length, that's the weight. That's a centrality score. Okay, so centrality score. So with that, let's take a 5-minute break. We finish on centrality. I'm going to come back and remember that thing about turning bipartite graph into the square graph, the connected adjacency matrix, adjacency graph. I'll show you a very important situation where that comes up. Okay, so let's take a 5-minute break.